Okay, so today we are going to discuss about these electric dipoles. Now, a electric dipole will consist two equal and opposite charges separated by a certain distance, which means initially like we will have two charges, one with plus q, then the other charge will be minus q. And there is a certain separation distance d between these two charges. So when we have two equal charges, magnitude is q, magnitude is q, but opposite in sign, plus and negative, separated by distance d. So this kind of a configuration, we can call it as a electric dipole. Now, if I place this electric dipole in an electric field, so let's say we have an electric field like this, then what will happen? Because of this electric field, there will be certain force acting on this charge and certain force acting on this charge. Then if these two charges are like, let's say these two are connected, then because of the forces acting on these two charges, this total configuration, this dipole will try to rotate. So there will be a torque acting on this dipole. Now we can see these electric dipoles in chemical compositions. So now, for example, if I take a H2O atom, so H2O atom will consist of a oxygen atom and two hydrogen atoms. So this oxygen will have a little bit of, not little bit, but with the uh, stable situation, in a stable situation. So oxygen and hydrogen here. So there will be negative and here will be plus and plus. But if I consider this as a one configuration, then this side will have a relatively negative charge here and this side will have relatively positive charge here. So this kind of situation we can consider as a uh, polar molecule which has a certain electric dipole here. Now, I think you can remember, I hope you can remember that we discussed what will happen in a microwave. So if I place this water molecule, if I have this water molecule in a continuously changing electric field, then this water molecule will rotate consecutively. And then because of that, each water molecule will collide with each another molecule. Then there is a certain kinetic energy and that kinetic energy will convert into temperature, thermal energy. That is how this food is going to be heated using a microwave. So we have many applications like this in when we consider about electric dipoles. Now, in our today's discussion, we are going to analyze these electric dipoles to calculate the potential and electric fields that will be generated using these electric dipoles. Now, first, let's find the potential at a point far away from a dipole. So it's going to be approximate value. So let's find the approximate potential at a point far from the dipole. Now we will consider a dipole with plus q and minus q. Let's say the separation is d, and we will calculate the potential due to this dipole at a point P. The coordinates here are r, theta, and psi. Then let's say vector connecting this point A and point P are A. Then the vector connecting point B and P are B. and we will calculate the potential from the midpoint of this dipole. So if that is the origin, then this is vector R, vector connecting the origin and point P. Now, how can we calculate the potential here? So if this distance is D, then we are considering the midpoint of the dipole. Therefore, this distance will be D over 2 from O to A. Here will also be D over 2. And let's say the angle here between the vector R and this AB line is theta. So the potential at point P due to this dipole, let's say that is V, this potential will mainly occur because of this plus charge and the minus charge. So with the plus charge, we have Q for 5 epsilon naught, and the separation from this plus charge to the point we are considering is RA. And then we have another potential because of this minus Q, and that is minus Q over 4 5 epsilon naught, and the separation is now RB. Now we need to calculate RA and RB. So let's say this R is also given, then we can use cosine law to calculate the RA and RB value. So we'll use cosine law. So in cosine law, we can state uh, the length facing this angle, it is RA. If I consider this OAP triangle, then RA squared is equal to, then the length between this angle R and D over 2. So R squared plus D over 2 squared minus 2 times this length and this length. R D over 2, then the cosine value of this angle, cos theta. Same we can write for the RB length. So RB squared is equal to R squared plus D over 2 squared minus 2 R D over 2. Now here angle is cos phi minus theta. Then RB squared is equal to R squared plus D over 2 squared. So cos phi minus theta is equal to minus cos theta. Then here will be plus 2. So 2 will be cancelled out. RD cos theta. Okay. Then we can use this. Let's say this is equation 1, equation 2, and equation 3. So we can use equation 2 and 3 to calculate 1 over RA and 1 over RB. So now we have, I'll use the equation 2 again. RA squared is equal to R squared plus D over 2 squared minus RD cos theta. Then now I want to find 1 over RA. So I will divide all these terms by R, and then I'll take RA over R. So RA over R is equal to, here when we divide this side by R squared, we have 1 plus D over 2R squared minus D cos theta over R to the power half. Okay. And same way, using equation 3, we should be able to get RB over R is equal to 1 plus D over 2R squared plus D cos theta over R to the power half. Now, we need to calculate the potential at a point that is far from the dipole. So, far from the dipole means R is going to be very large relative to D. R is very large than D. So, what will happen when R is very large than D? Then, this term will reach 0 when R is very large than D. Okay. Therefore, we can write RA over R is equal to, so when we are considering R is very large than D, in that case, RA over R is equal to 1 minus D over R cos theta to the power half. Then 1 over RA, 1 over RA, so I'll say R over RA is equal to 1 minus D over R cos theta to the power minus half. Okay. Thereafter, 1 over RA distance is equal to 1 over R times 1 minus D over R cos theta to the power minus half. And if we write the Taylor expansion for this term, 1 minus D over R cos theta to the power minus half, then since R is very large than D, then this will be approximate to 1 over R. This term will be approximated to 1 minus D. So power is minus half D over R cos theta. And we will have like other terms, those will be D over R square, D over R to the power higher order powers. So those terms will go to 0 when we consider R is very large than D. So in tail expansion, we can consider only this term will be remaining when R is very large than D. In the same way, we can write 1 over RB, it is approximately equal to 1 over R, 1. And now for the RB, we have here plus minus half D over R cos theta. So this is equal to 1 over R 1 minus d over 2r cos theta. And Ra is equal to 1 over r 1 plus d over 2r cos theta. Then we can apply this 1 over Ra and 1 over Rb to the potential that we need. So that equation 1 is this. So potential is equal to Q over 4 pi epsilon naught Ra minus Q over 4 pi epsilon naught Rb. Now the potential is equal to Q over 4 pi epsilon naught Ra minus Q over 4 pi epsilon naught Rb. So it is equal to Q over 4 pi epsilon naught 1 over Ra minus 1 over Rb. Then the potential here is equal to Q over 4 pi epsilon naught 1 over R. So we have for the Ra, it is 1 over R times 1 plus d over 2r cos theta minus 1 over r. Rb is 1 over r. So 1 over Rb is equal to 1 over r times 1 minus d over 2r cos theta. Then by simplifying this, you can get the potential is equal to Q over 4 pi epsilon naught. So 1 over r is common here and here. We have 1 plus d over 2r cos theta minus 1 plus d over 2r cos theta. So minus 1 plus 1 cancels out. Then we have d over 2r cos theta plus d over 2r cos theta. So it is equal to now here we have 1 over 4 pi epsilon naught. We have q d cos theta over r square. So this is the potential at a point that is far from the dipole. Potential is equal to 1 over 4 pi epsilon naught qd cos theta over r square. Okay. So you can take notes out of this. And now what we did is we look for an approximate value for the potential at a point that is far from the dipole. So we consider this point P. Here is coordinates are r, theta, and psi. So vectors connecting plus Q and the point P are Ra, minus Q and P are B, and the center of the dipole O and P is R. Then we have mainly these two charges plus Q and minus Q affecting the potential here. So we wrote the equations for those two potentials. From plus Q, we have Q over 4 5 epsilon naught RA plus from minus Q over 4 5 epsilon naught RB. In the potential, we can take the common factors out. Q over 4 5 epsilon naught RA 1 over RA minus 1 over RB. Then we need to calculate this 1 over RA and 1 over RB to have a value for the potential. Then we used cosine law for this OAP triangle and OBP triangle. So when I first consider this OAP triangle, here the angle is theta. The length directly facing the angle RA squared, we can write using the cosine law. RA squared is equal to R squared plus D over 2 squared minus R times D over 2 times cos theta. So that is using cosine law. So we wrote those equations. And then since we are looking for a point located very distance from this dipole, in those cases R is very large than D. Then by considering the Taylor expansion, we further simplified this into this form. 1 over RA is approximately equal to 1 over R times 1 minus half times D over R cos theta, and 1 over RB is approximately equal to 1 over R times 1 plus minus half times D cos theta over R. And then we calculated 1 over RB and 1 over RA minus 1 over RB. So, and then we were able to finally calculate the potential by substituting this value for the initially obtained potential value. It is equal to 1 over 4 5 epsilon naught Q D cos theta over R square. So any question up to this point? Is this simplification clear to you, or any questions? Anything? So if you have any questions, you can raise your hand, or otherwise you can chat, or you can talk, you can speak. Okay. And then now when we have a one charge, we can call that a monopole. And now when we had two charges with the same magnitude, but with opposite signs, plus and minus, we call that a dipole. And also we can have quadrupole and octopole, like those situations. Here, four charges and same magnitude, but charges, sign of the charges are arranged in this way, plus minus, then same way. In octopole, we have 8 charges, and all the charges should have the same magnitude, but the arrangement of the sign minus, plus, likewise. In a certain order, this sign of the charges are arranged. And when we have a monopole, we observe that potential is proportional to 1 over R. In a monopole, potential is proportional to 1 over R. Now, in a dipole, we observe potential is proportional to 1 over R squared. Then in a quadrupole, where we have 4 charges, potential will be proportional to 1 over R cube. In an octopole, potential will be approximately proportional to 1 over R to the power 4. Okay. Likewise, we have monopole, dipole, quadrupole, and octopole. We have many other arrangements. And then I mentioned to you, because when we have this kind of a dipole, there will be a certain torque that can be occurred on this dipole when we place this in a electric field. And then we can use dipole moment to quantify that and also to see whether we have a certain polarity or whether a certain molecule is a polar molecule or non-polar molecule. For those situations, we can use this calculated dipole moment there. Now, when we are calculating dipole moment, now in an electric dipole, we have plus Q and minus Q. So this will be separated by a certain distance d. The electric dipole moment P can be calculated by Q times d. So in here we need to consider the distance d in a vector format. And the distance d, the direction vector d is in, the direction is from minus Q to plus Q. So the direction is minus Q to plus Q. So if you have two dipoles, P1 and P2, then the total dipole moment can be calculated by considering the vector summation of these two dipoles here. Now, if I look for a arrangement like this, so here minus Q plus Q, and here minus Q and plus Q, minus Q plus Q, minus Q and plus Q. So how many dipoles we can identify here? How many dipoles can we identify here? So type in the chat how many dipoles we can identify in here. How many dipoles are here? Is it one, two, or how much? Okay. Yes. So there are 4 electric dipoles we can identify with this plus Q and minus Q1 here. And then with this plus Q and minus Q1 here, then if I take this plus Q another dipole and this plus minus another dipole. So when we are calculating the total dipole moment, we need to consider in vector format. So the total dipole moment in this situation, we have a one dipole, so minus Q to plus Q. Here, let's say this is length A and this is length B. So we have Q times A, and then if we consider these two, then that will be Q times minus A. Then for here, minus Q to plus Q, we have Q times B. Then again, from this minus Q to plus Q, we have Q times minus B. Then the total dipole moment, net dipole moment is going to be 0 in this situation. Okay. So if you have 2 or more dipoles, then the total dipole moment can be calculated using considering the vector summation of those dipoles. Now let's try this one. So we have an electric dipole plus Q and minus Q, and we need to calculate the dipole moment at a point P. Angle here is theta with a distance r. We need to calculate the potential here, and potential we should be able to say potential is equal to P dot R over 4 pi epsilon naught R square. So take few minutes and try this one. we know the dipole moment is equal to q times d, and we also know how to write the potential at this point P. So previously, for the potential we obtained, when we consider a distance r large than r is very large than d, then the potential can be write using 1 over 4 pi epsilon naught q d cos theta over r squared. Now let's calculate this p dot r and see what is the value we are getting there. So p dot r is equal to magnitude of p, magnitude of r unit vector, and the so here the direction of the dipole moment will be minus q to plus q, like here. So it will dipole moment of direction of the dipole moment will have the direction of the direction vector. So direction vector is here, therefore dipole moment will also be in this direction, and the angle between the dipole moment vector and the r vector is theta. So p dot r is equal to magnitude of p, magnitude of r cos theta. Now here we will have magnitude of p, and what is the magnitude of a unit vector? What is the magnitude of a unit vector? It will be 1. So here we will have cos theta. P dot r is equal to this value. And the magnitude of this dipole moment we can write q times d magnitude cos theta. So we have q, magnitude of d is d cos theta. Now we have p dot r is equal to qd cos theta. Then we can write potential. Potential is a scalar. It is equal to, now qd cos theta is equal to p dot r. Therefore, potential is equal to p dot r over 4 phi epsilon naught, and we have 1 over 4 phi epsilon naught. Now we showed that qd cos theta is equal to p dot r. Then we have 1 over r square. Now potential is equal to p dot r unit vector over 4 phi epsilon naught r square. Also, we can write this one. Now we have the p. Let's first write this one. 4 phi epsilon naught r square p dot r unit vector. So r unit vector, if we have a r vector, uh, then we can so r unit vector if we have a certain vector r, then by dividing this vector by its magnitude, we can get the unit vector in that direction. So unit vector r is equal to vector r over the direction over the magnitude of that vector. So in that case, potential is equal to, now we have P dot R over 4 pi epsilon naught. Here we had R squared, now R squared times R to the power 3. So potential in a dipole, we can calculate using this equation 2. Okay. Now the given question is to show that potential is equal to show that potential in a dipole, we can we can write that in related to dipole moment and the vector connecting the midpoint of the dipole and the point we are interested. So we initially obtained this equation, potential where distance from a dipole is equal to 1045 epsilon naught qd cos theta over r squared, and we uh, discussed dipole moment is equal to qd, and then we first calculated this p dot r and showed that p dot r p p vector dot r unit vector is equal to qd cos theta. So qd cos theta, here we have that. Then we can write the potential as 1 over 4 pi epsilon naught p dot r unit vector over r squared. And also we can calculate a unit vector by dividing the vector in that direction by the magnitude of that vector. So r unit vector is equal to r vector over the magnitude of that vector. Then potential is also equal to dipole moment times dipole moment dot r vector connecting the midpoint of the dipole and the point we are interested over 4 pi epsilon naught times r to the power 3. Okay. And then we can, once we know the potential, we can calculate the electric field using this equation that we discussed earlier. So let's calculate the electric field intensity in spherical polar coordinates. Now we know the potential, then we need to calculate the electric field. So electric field E is equal to minus gradient of this electric potential del V. And if you want to use the spherical polar coordinates, in spherical polar coordinates, del operator is equal to dabba over dabba r hat plus 1 over r dabba over dabba theta hat plus 1 over r sine theta dabba over dabba theta dabba over dabba psi hat, and we have the potential. It is a scalar function, so we can include that all these partial differentiations. So if I say this electric field will have R component and theta component, and psi component. So let's calculate each of these components. Now the potential we have potential is equal to P dot R hat over 4 pi epsilon naught R squared. So this, we cannot see any dependence of this psi. And if I write this, so we have the dipole and angle here is theta, and this is the R vector and the direction of the R in this direction, and we have the dipole moment in this direction. So we can write P dot R is equal to magnitude of P, and here unit vector R hat cos theta, angle between these two vectors, over 4 phi epsilon naught R square. So this is equal to P cos theta over 4 phi epsilon naught R square. Now the potential, if we look into this equation, we cannot see any dependence of psi, but we have a dependence of theta and R. Then once we do the differentiation, we can calculate dabba V over dabba R. It is equal to now P cos theta over 4 phi epsilon naught, and we have minus 2 over R to the power 3. Then minus dabba V over dabba R, it is equal to P cos theta over 2 pi epsilon naught R to the power 3. Same way, 1 over R dabba V over dabba theta, we can calculate by taking the differentiation of this term. And then, so here it should be minus, and once you calculate those two terms, we can write the electric field due to this dipole. Is equal to E is equal to P cos theta over 2 phi epsilon naught R cube in the direction of R, plus by calculating this term, you should be able to get P sin theta over 4 phi epsilon naught R square in the direction of theta. So this is the electric field in spherical polar coordinates. So that calculation is also given here. In spherical polar coordinates, we can write the del operator in this way, and V is a scalar function. Therefore, gradient of that scalar function we can include in all these terms. And then we don't have any dependence of psi for the potential, and we only have dependence of theta and R for the potential. Then we can calculate ER and E theta. Then we can write the electric field in this way. So same thing, P over 4 phi epsilon naught R to the power 3 to the power 3. This answer should be correct. So P cos theta, okay, but here it should be R to the power 2. So this answer should be correct, and check whether you are getting this answer. And also we can do the same calculation in Cartesian coordinate system. Now in Cartesian coordinate system, same potential is equal to P dot R over 4 phi epsilon naught R to the power 3. And then in Cartesian coordinate system, we can write the dipole moment. P is equal to, if we locate plus q and minus q in the Z direction, then we can write dipole moment P is equal to P in the direction of K, and R, the coordinates of this point P, is equal to, so coordinates of the point P is equal to X, Y, and Z. Therefore, distance from the origin to that point P is equal to X square plus Y square plus Z square square root. Then potential at that point is equal to P dot R is equal to P dot Z, because now the R vector is Xi plus Yj plus Zk. Then P vector is Pk, and when we take the dot product, only the remaining will be Pz. So we have the Pz here, P dot R, Pz over 4 pi epsilon naught, R to the power 3. So R is this, then that to the power 3, this value. So we can calculate the potential in potential and electric field due to a dipole in Cartesian coordinates in this manner. And then the electric field and the potential is written in this equation. So del operator here in Cartesian coordinates. And when we look into the potential is now depending on X, Y, and Z. Therefore, we will have all these Ex and Ey and Ez components. By doing the differentiation with respect to X, Y, and Z, we can calculate Ex, Ey, and Ez. And then we can write the electric field in this manner: Exi plus Eyj plus Ezk. Okay. And so write down this question and try that one as a homework. Four particles with charge Q four particles with charge plus Q, minus Q, 2Q, and minus 2Q are placed as shown in this figure. So I have plus Q here, minus Q here, and minus 2Q here, and plus 2Q here. Each is distance, each located at a distance A from the origin. So from origin to this plus Q distance A, plus 2Q distance A, minus 2Q distance A, and minus Q distance A. Find an approximate formula. So we don't need the exact value, we need an approximate value for the potential valid at a point far from the origin. So if I consider a point very distance from the origin, so what is the potential at that point? So we need an approximate value for the potential at that point. So try out this question and write down this one, and you can do it as a homework. Okay.